Good morning, everyone. This is M. Pawan from IRE College, Data Science Branch, B section. Now I am here to explain you one concept of in physics, applied physics, Stefan Boltzmann law. Today in our session, we are going to learn how, what is this law and how it is useful in our life. So we will move on to our next slides to learn more about this. Introduction. Joseph Stefan was an Austrian physicist. In 1879, he formulated a law about the radiant energy of a black body. According to the law, a theoretical object that absorbs all the radiation that fails that fails on it is proportional to the fourth power of its temperature. His law was one of the first important steps toward the toward the understanding of the black body radiation, from which raised the quantum idea of radiation. Stephen rose from a lecturer in the subject of mathematical physics in 1858 to a professor ordinarius of physics in 1963 and to the director of the Physical Institute in 1866 at the University of Vienna. 5 years later, he derived his law empirically. The same was derived theoretically by Ludwig Boltzmann of Austria and hence become known as the Stefan Boltzmann law. Black body radiation. A theoretical object that can be perfectly efficient at observing the emitting radiation is known as a black body, and it therefore emits what's known as black body radiation. A black body is black at room temperature, hence the name. However, at high temperatures, it can actually glow at visible wavelengths. Therefore, we should be aware that astrolo- astronauts and physicists use the term black body to also refer to objects that glow. Naturally, we may tend to think that black body radiation is given off only by hot objects like that hot metal rod or an extremely hot star. Not so. The radiation that is emitted by a heated body is termed as black body radiation, but heated in a relative term. What I mean is it's heated when compared to absolute 0 Kelvin minus 273.2 Celsius or minus 273.2 Kelvin or minus 459.7 Fahrenheit. Knowing this, it won't surprise you to learn that blackbody radiation is emitted by everything from stars, light bulbs to ice cubes. That's because at temperatures above absolute zero, particles in an object still have thermal energy and thus radiate photons. An ice cube may be as cool as a cucumber, but compared to absolute zero, it's as ignited and hot as you are when your computer freezes or the car doesn't start. Why does hotter is equal to brighter? Now we need to learn how the temperature and the color of the glow of an object interact. Surely you have seen how as metal is heated more and more, it actually changes the color of light. It emits from red to orange to yellow as it gets hotter. Now you learn why it changes color and gets brighter as it gets hotter, not just why it glows. Firstly, the hotter an object is, the more blackbody radiation is emitted by it. Why? Well, the madder you are, the madder you are, the more ignited you are. The more steam you have to blow off, the hotter an object. The more collisions there are, the more violent those collisions, and the more radiation is emitted. This is why, as things get hotter, they get brighter. What is absolute temperature? The absolute temperature of an object is the temperature on a scale where 0 is taken as absolute 0. This is also known as thermodynamic temperature. Absolute temperature scales are Kelvin, degree units Celsius, and Rankine degree unit Fahrenheit. Absolute zero is the temperature at which a system is in the state of lowest possible energy such that minimum energy. When molecules approach its temperature, their movement drop towards zero. It is the lowest temperature that a gas thermometer can measure. You know, electric devices will not work at this temperature. Finally, the kinetic energy of the molecules becomes negligible or zero. Common temperatures as seen in the absolute scale are 0 degrees Celsius is equal to 273.15 Kelvin, 25 degrees Celsius is equal to 298.15 Kelvin, 100 degrees Celsius is equal to 373.15 Kelvin, 0 Kelvin is equal to minus 273.15 Celsius, 232.15 Kelvin is equal to minus 41 Celsius. To convert from the Celsius scale into the absolute temperature, you have to add 273.15 and change in degrees to Kelvin. To get a temperature on the absolute scale to the Celsius scale, you have to subtract or minus 273.15 and change K to 0 degrees Celsius. This is generally used in the world of science. Kelvin is used globally. It is one of the 7 base units of the system. The value of absolute temperature is 0 Kelvin. Conversion of units of temperature. Celsius to Kelvin. K is equal to C plus 273.15. Kelvin to Celsius. C is equal to K minus 273.15. Fahrenheit to Rankine. R is equal to F plus 459.67. Rankine to Fahrenheit. F is equal to R minus 459.67. Applications of Stefan Boltzmann law. The Stefan Boltzmann law describes the power radiated by a body that absorbs all radiation that falls on its surface in terms of its temperature. The radiation energy per unit time from a black body is proportional to the fourth power of the absolute temperature and can be expressed as the following formula. Radiant energy is equal to Stefan Boltzmann constant into temperature per 4. The equation is J is equal to sigma T power 4 J meter inverse to second inverse 1. J energy radiated per unit area by a black body per unit time. Units J meter inverse to second inverse 1. Sigma Stefan Boltzmann constant value 5.67 into 10 to the power minus 8 joule second inverse meter inverse to Kelvin inverse 4. T absolute temperature units Kelvin. A body that does not absorb all the radiations that are incident on it are known as a gray body, which emits less total energy than a black body and is characterized by an immensity. J is equal to sig E, E sigma epsilon sigma T power 4. The radiant emittance J has the dimensions of energy flux, energy per time per area, and the SI units of measurement are joules per second per square meter, are equivalently watts per square meter. Kelvin is the SI unit for absolute temperature T. Epsilon is the immensity of the gray body. If it is a perfect black body, E is equal to 1. To find the total radiated power from an object, multiply the formula with its surface area A. P is equal to J into A. A is equal to A epsilon naught sigma T power 4. Radiation energy power can be represented as following. Radiate energy is equal to emittivity into Stefan Boltzmann constant into temperature power 4 into area. The equation is P is equal to sigma epsilon naught sigma T power 4 A watts. Pictorial representation of Stefan Boltzmann law. Check out the graphs below representing black-body curves. To see this concept represented visually, note that these graphs have a y-axis indicating intensity and an x-axis representing wavelength. You see larger areas under curves representing hotter objects, where the area under the curve is proportional to the total energy emitted. So a hotter object emits more radiation, including visible light. This concept refers to the Stefan Boltzmann law, which says in simple terms that the total energy radiated from a black body is proportional to the fourth power of its temperature. What is Stefan Boltzmann constant? The Stefan Boltzmann constant symbolized by the lowercase Greek letter sigma is a physical constant related to Blackbody radiation. The constant defines how much power a blackbody can emit per unit area as a function of its thermodynamic temperature. Stephen's law establishes the relationship between the emitted power per unit area in watts per square meter, the thermodynamic temperature in kelvins. This means the power per unit area is directly proportional to the fourth power of the thermodynamic temperature. Thus, the value of the Stefan Boltzmann constant is approximately 5.67 into 10 to the power minus 8 watt per meter square per Kelvin to the fourth. Example: a body having a density of 0.1 and its area is 200 meters square at 500 Kelvin. Find at what rate does it radiate energy. The energy radiated is given by the formula P is equal to epsilon sigma T power 4A. 0.1 into 5.67 into 10 to the power minus 8 watt meters square Kelvin per 4 into 500 Kelvin per 4 into 200 meters square. That implies P is equal to 7.08 into 10 to the power 4 watts. I hope everyone understand this concept and this example, and thank you for giving me this wonderful opportunity to explain my knowledge with you. I hope everyone enjoyed my session. Thank you.